హలో ఎవ్రీవన్, పబ్లిక్ ఎగ్జామినేషన్లో క్వశ్చన్ నెంబర్ 23 మనకు ప్రాబబిలిటీ టాపిక్ నుంచి ఒక లాంగ్ ఆన్సర్ క్వశ్చన్ ఫ్రేమ్ చేస్తున్నాడు. రిపీటెడ్గా అడిగిన క్వశ్చన్ స్టేట్ అండ్ ప్రూవ్ అడిషన్ థీరం. లెట్ us see this. The question state and prove addition theorem on probability. First you have to write the statement and then you have to prove. Suppose that there are two events, capital A and capital B. If A comma B are two events in a sample space S, and P is probability function, then probability of A union B written as P of A plus P of B minus P of A intersection B. This result you have to prove now. Yes, to prove this, two cases arises. First, case 1. Suppose the two events capital A and capital B are disjoint, and in the second case suppose that they are not disjoint. What I am saying, case 1, if capital A comma capital B are disjoint sets. Disjoint implies we can write their intersection part is empty. Implies automatically probability of A intersection B become 0. And the diagram in this case, suppose that this is sample space S, in which you have to select two events and the events must be disjoint. Suppose this is first one. Next, suppose this is second one. Assume that this is A, event A and event B. Clearly there is no common part of A and B, so that they are disjoint. And now by axiom of addition, by axiom of additivity, I can write probability of A union B, that is very clear, they are disjoint, so that I can write P of A plus P of B. Now what I am doing, observe. Yes, in the next step I can write P of A union B as P of A plus P of B minus 0 I can write, that is P of A union B equal to P of A plus P of B minus P of A intersection B you can write. This is obvious. This is the first case, right? Let us move to the second case. In the second case, you have to select A comma B are non-disjoint. Case 2 I am going to write, if suppose A comma B are not disjoint. When A comma B are not disjoint implies I can write their intersection part is not empty, and hence the diagram become yes. I am going to select non-disjoint sets. This is A and this is B. Suppose that here it is capital A event and this is capital B event, and there is a common part of both the events A and B. Now from figure here I can write the set B, that is the event B. I can write event B is union of this is the portion intersection part, A intersection B part this is, and next and this one is the portion called as B minus A. Therefore I can write the event capital B or the set capital B as first A intersection B union, I can write B minus A, and here these two are disjoint, remember, since A into B and B minus A, they are disjoint. Whenever two events are disjoint, by axiom of additivity I can write probability of A union B, P of A plus P of B. Therefore here I can write probability of union of these two. Therefore you can write probability of A intersection B, first one, union B minus A, that can be written as first probability of A intersection B plus probability of B minus A. But this one is clearly B. Therefore P of B written as probability of A intersection B plus probability of B minus A. And you can write probability of B minus probability of B minus A, that is probability of A intersection B. Assume that this is some star. Next, yes, I am going to write A union B part. See here, A union B. A union B part written as A union B minus A, you can write A union B minus A. A is, this is A part, and for this A, if B minus A is added, then we get A union B, right? And here A and B minus A are disjoint. A comma B minus A are disjoint in this case. When they are disjoint, union can be written as addition by axiom of additivity. Therefore I can write probability of A union B minus A written as P of A plus P of B minus A. But A union B minus A is A union B. Therefore here I can write probability of A union B, it is equal to P of A plus P of B minus A. Now you can replace probability of B minus A with star. From star, probability of B minus A you can replace. That is probability of A union B equal to P of A. From star, what is probability of B minus A? That is P of B minus P of A intersection B. So that here we get P of B minus P of A intersection B. Yes, this is result 2. From 1 comma 2 it is clear that in the next step I can write finally you have to express this one from 1 comma 2. From both the cases it is clear that probability of A union B equal to P of A plus P of B minus P of A intersection B. Hence the theorem proved. This is about addition theorem of probability. Yes, next question. State and prove Bayes theorem on probability. Bayes theorem is also called as inverse probability theorem. And you have to write the statement as well as you have to prove that. I am going to write the statements. Suppose E1, comma E2, comma E3 and so on En are n mutually exclusive and exhaustive events. These n are mutually exclusive and exhaustive events. And suppose that P of A more than 0 such that A is an event of all EI. Then you can write the statement probability of Ek divided by A equal to denominator part summation probability of EI, probability of A given EI, I value from 1 to n, and in the numerator probability of Ek multiplied by probability of A by Ek. This is the statement of Bayes theorem of probability. Now we need to prove this result. See here, E1, E2, E3 and so on En are n mutually exclusive and exhaustive events. Here the figure indicates event 1, event 2, event 3, event 4 and so on. This is the last event En. And probability of A more than 0 such that A is an event of all EIs is given. Yes, this is suppose that A an event, it is for all E1, E2 and so on En. You know that mutually exclusive means their intersection part is empty. EI intersection EJ. Whatever the events you choose, they are disjoint, remember. And exhaustive means here union of E1, E2, E3 and so on En, that indicates sample space S, remember. This is sample space S. So I am going to write the proof. Since E1, E2, E3 and so on En, they are mutually exclusive, implies I can write EI intersection EJ is empty for all I, j 1 to n. Next, I am going to write, since E1, E2, E3 and so on En, they are mutually exclusive. Exclusive implies I can write E1 union E2 union E3 union and so on union En, that is equal to sample space S. This is result 2 and this is result 1. Next, given that A is an event of all EI, yes, here I can write A as A intersection S. A intersecting with S. What happens? That become automatically A. Why? Because S is here, S is sample space and A is smaller part in that. So A intersection S again A. This is from figure. Implies I can write A value, A intersection S. From 2 I can write E1 union E2 union E3 and so on union En it is. In the next step I can write A as A intersection E1 first one plus union, next A intersection E2, next in between them union symbol and so on union A intersection En you can write. A intersection E1 portion, see here A intersection E1 portion you have here, this is A intersection E1 portion. Next A intersection E2 you have here, this is A intersection E2 portion. Next A intersection E3 that you have here, and these are all clearly disjoint. Since they are disjoint, A intersection E1, A intersection E2 and so on A intersection En, they are clearly disjoint. Therefore, if I apply probability by axiom of addition, I can write probability of A become probability of A intersection E1 plus probability of A intersection E2 plus and so on plus probability of A intersection En it is. And you can simply write this one as summation probability of A intersection Ei, right. Next I can write LHS part. I am going to write, you have LHS probability of Ek given A. By condition probability, I can write in the numerator probability of Ak intersection A divided by probability of A. Yes. Next, this is equal to, in the denominator part P of A you have summation probability of A intersection Ei, this is, and this is probability of Ek intersection A, and from this you can, now this is probability of Ek given A equal to, it can be written as numerator probability of Ek multiplied by probability of A given Ek, and this is with summation symbol, summation probability of EI, probability of A given EI you can write, where the value of I from 1 to n. Yes, this is the proof of base